probability based GRE model that is very popular for engineering, and I'll explain in detail. So a little, I'm not giving much about the theory, so we'll go only the application part, how we can use for our engineering applications. So the gray system theory, so it is a part of the information is known and the part of the information is unknown. So with this definition, information quality or the quantity is continuum from the total lack of information to the complete information. So it changes from lack of information to the complete information. So what we can say, from black to gray, then white. So when we can say black, without any information. When we can say white, when we'll have the complete information. But in reality, we'll have only the gray information. And when we are saying this gray, so there is a uncertainty. So right, one always somewhere in the middle. So we'll not have in the black side and we'll not have the white side, and we'll have only the gray side. Because of the, we'll have the uncertainty. So we cannot say I don't know anything. At the same time, we cannot say I know completely. Right? So that is uncertainty. So because this uncertainty exists, so we'll always will be in the middle. So which side we, so it may be varies, right? How much you know and how much you don't know, right? So the great analysis comes to a clear set of statements about the system solutions. At one extreme, no solution can be defined for a system with no information. At other extreme, a system with perfect information has a unique solution. So when you know the perfect information, then we'll have the unique solution. But what will happen in the reality, we don't know the perfect information. So whatever we'll get is not the exact solution. I'm repeating once again, in all our engineering applications, most of the cases, what we will do, we will try to approach the nearest exact solution, right? And how much near we are getting, that depends upon the what is the accuracy, right? So you never achieve the exact solution, so which is unique solution, but you never achieve, right? So we'll achieve only the nearer to the exact solution. So in the middle, the gray system will have the variety available of the solution. And what is our strategy? Our strategy is to take the best solution based on what is the knowledge available to us. So the gray system does not attempt to find the best solution, but does provide only the techniques for determining the good solution. So that is the difference between the best solution and the good solution. So what we are achieving is a good solution. So best solution is only one, right? Still we will write, while writing our papers and other things, we'll mention this is the best solution. What is our contest there? Our contest is in the availability of number of experiments what we conducted, or availability of the information what we have. From that it is best, right? Because we'll have, already I told, we'll have the uncertainty. So we don't know the complete information. So perfect information is impossible, right? According to our information, what is available to us, according to the number of experiments we conducted, right? According to the results obtained, from that, what is the best solution? So it is best for us, but in reality is a good solution, right? So that is the difference between the best solution and the good solution. So what we are getting is only good solution, but still we'll claim it is the best among the what are the information available to us, or what are the experiments we conducted and based on the results obtained, right? So that is the applications. The theory has applied for the various fields of engineering and management. So management also, I told I'll give one or two examples, right? And initially the gray method was adopted for effectively the study of air pollution, and subsequently used for non-linear and multiple dimensions for socio-economic actors of the impact on the city air pollution. So that part we are not discussing. We are discussing only the what are the ways we can use for engineering applications. And these are the some journals where we want to publish, and this is pure relational analysis. And most of our cases we may not go to this, because when we want to develop a new concepts in the gray relations, then only you can publish in these journals, or it may be depends. But what we'll publish in our journals is some measurement, some expert systems and applications. So some of the journals are there where this approach, the gray relation approach, you can use for your experiments, and you can get your research will be published. But you can try these journals. These are the journals purely on gray systems, right? That is a journal of gray systems, and we'll have the gray system theory and applications. So this is totally focusing on developing of the gray system theory and the applications. The impact factor is very high, it is 3.3. And we'll have the International Journal of Gray Systems and Journal of Gray Systems, that is from Taiwan, and the Gray Journal and Journal of Intelligent and the Fuzzy Systems. So these are the journals totally focusing on the gray analysis. but we'll have so many other journals where we can publish our research work, right? So if you are able to develop some new concepts in the gray system itself, in the theory itself, so the fundamental concepts of the gray systems, you want to develop a new thing, so you can go for the publication of this one of the journals. Only application part you can use, you can publish in other journals, measurement and other journals are there, and any other journals, good journals, they'll publish when you use these concepts. I'm audible to you? Shall I increase my voice or lower my voice?
Yes, sir, it is audible properly.
It's properly, okay. Okay, now what are the steps involved in the gradient analysis? So these are not universal steps, you can modify according to your wish. So first one is the initialize the features. Either we'll get information from the experiments or from any other source. Then we'll have the normalize the features. I'll tell what is the need for the normalize while explaining one of the problem, and define the ideal conditions, right? Ideal values, and then we'll calculate the gray relation coefficient. Next stage is we'll calculate the gray relation grade. So once you are getting the gray relation grade, right, then we'll rank the features based on the gray relation grade. So once you are giving the rank, which is having the first rank, that will choose the best feature. So these are the steps involved. I repeat. So first we'll have the initialize the features, right? So we'll get the information, right? Then in the form of the data, right? That may be either from the data books, or you can get from the conduct the experiments, the output of the experiments, the responses. Then we'll have the normalize the features based on we'll define the conditions, ideal conditions. Then we'll calculate the gray relation coefficient. Then we'll calculate the gray relation grade, and based on the gray relation grade value, so match the properties are then shortlisted. So we'll select the materials and what are the properties required for a particular application. So what you are designing and where it is going to apply, right? And what are the properties needed for that part based on the application. Then we'll select the materials. Then we'll shortlist the materials. We will not use all the materials, we'll shortlist. So these are the materials I can use. Then the doubt is which material I have to select. So we'll have some group of materials. So it is not that much easy task. It is very tedious task, right? So we'll have some properties. We are designing a new product or any product. So it will have some applications. So based on that application, we'll select the material properties. So once we select the material properties, then we have to see which are materials matching nearer to matching these properties. Then we have to shortlist, right? So that is the first stage. And the second stage will go for the data pre-processing. The data collected from the various material properties have different dimensional units. So whenever you are collecting the data, so you'll have the different dimension units. Suppose you are talking about the hardness, brilliant hardness, it will have its own units. Ultimate tensile strength, it will have its own units. Right? So they will have the different units and they will have the different numbers also. One will be in the order of thousands, another will be in the order of 10, 20. Right? So we'll have the different material properties, will have the different dimension units. Then what we have to do? We have to do processing of this information. So that is called the normalizing. So in the steps I told we should have the normalization. So because we'll have the different material properties, we'll have the different dimensional units as well as the different values also, numerical values also. One will be in the thousands, another will be 10,000, or one will be in the fractions also, or the 0.1, 0.2 like that. Right? So then what we have to do? So this all we are making in between 0 to 1. So there is some steps are there, how we can make these values ranging 0 to 1. So that is to make them dimensionless and comparable. Then only can compare. Otherwise you cannot compare. One is in 10,000, other is in fractions, 0.1, 0.2. So you cannot compare. So to make the comparison and to make the dimensionless, we are making into the value should be in between 0 and 1. Right? So that is the reference is given. If you want, you can go for the reference. Right? So data can be normalized based on the 3 different formulations. How we can normalize? Right? So we will have the specific criteria. So what is the criteria? Some of the properties or some of the cases you want, the larger the better is important. Some properties we want, the smaller the better. And some properties will have the nominal value, means we'll select some target value. It should be nearer to the target value. Right? So we'll have the 3 conditions are there. Some cases you want the larger the better. Some cases you want the smaller the better. Some cases you want the nominal the better. Some properties you want should be higher values. And some properties you want the lower values. And some properties we want the some targeted value. So generally for engineering application we'll go for either larger or the smaller. Right? So rare case we'll go for the targeted values. That is nominal value means. So we'll fix some value and it should be nearer to that value. Then we'll use the 3 different equations. Right? So we'll have the first equation that xi of k minus minimum of xi of k. So we'll take the minimum available value. Denominator is the difference of maximum value and minimum value. Right? Suppose you have any data is there. So let's select that value minus in that data what is the minimum value. And the denominator will be the difference of maximum and minimum values. So that equation will use when the larger is the better. And when the smaller is the better, then we'll use the second equation. That is the maximum value on the available data minus particular value. Denominator again will be the maximum minus minimum, the difference of the maximum and minimum values. And when we'll have the third condition, that is the nominal, or we are selecting some targeted value, right? Then it is 1 minus modulus of xi of 0k minus x0. So that is x0 is the targeted value, right? Suppose you are fixing some targeted value, some 150. So that x should be 150, right? And why I kept here modulus? In the first 2 cases it is not modulus, second case it is a third case it is modulus. Modulus means sometimes the target may be above the target value or below the target value. So we'll the negative. So in order to avoid the negative, we are keeping the modulus. Right? That is only the reason why you are keeping the modulus here. Right? Sometimes this value will be more than this or it can be less than this. So we may get the positive value or the negative value, but we want it should be only the positive. So that is the reason equal to here modulus. But this is the rare cases. So one case I can give in the case of the delamination of composite materials. You want it should be 1. So there it should be targeted value is 1. Right? So in some cases only we'll go for the fixed values. In general we'll go either the larger is better or the smaller is better. Right? Either we'll use the first and second case. Right? The same thing is explained here. Then the next step is the determination of the correlation coefficients. So here we'll use the equation delta minimum. So for that what we'll do, here the important concept is there. So we are getting the normalized data. And before this, so we'll make the deviation sequence between the reference and comparability sequences. Right? So the reference sequence and comparability sequence, so we'll make the deviation. Right? So what we'll do after the normalized values you are getting, then we'll subtract with minus 1. 1 minus normalized value, that is called deviation. Means how much they are deviating from the ideal value, means from the normalized value. So that is called deviation sequence. It is denoted by delta. Right? So what we'll get after getting the normalized value, then we'll find the delta, means how much they are deviating from 1. So 1 minus the normalized value will give the delta values. Then we'll calculate the correlation coefficients. So the formula for the find the Gradient coefficient is eta of k is equal to the delta minimum, that is the deviation. Already we are getting the deviation values. So in that, what is the minimum, right? Delta minimum plus eta into delta maximum, right? So this is eta into delta maximum. So in that deviation values, what is the max value? And the denominator is delta of 0 ik, means particular element what you are using, plus eta into delta max. So here the numerator will be the common for all the values, for all the rows or the columns, rows, and the denominator will be varying, right? So delta k is the deviation sequence between the reference sequence and the comparability sequence, and eta is called a distinction or the identification coefficient. So it is the identification coefficient, and general will keep it is 0.5. General will keep this value is 0.5. Right? So I'll explain. If you are select, you may have the doubt why you should select 0.5. I can use 0.4 or 0.3 or 0.1, and never don't keep 0. So I'll explain with the problem what will happen when you are keeping the other values. But generally, to solve the problem, we are keeping 0.5. Means, are assuming we know 50% of the information, like that. That is the reason. And you can change the value also. It is not necessary to use only 0.5, because some of the journals use 0.5. I also use 0.5, but there is not mandatory, right? You can use 0 to 1, but don't use 0. So when you use 0, both total becomes 0 by 0, right? Because it becomes 0 here, and delta minimum is 0 generally, right? So then what will happen? So it comes numerator becomes 0. So don't use 0. You can use any other value, right? If possible, you can use 1 also, but generally we are using 0.5. So then by using these equations, we are trying to determine the gradation coefficient. Then we'll calculate the gradation grade. So the gradation grade can be determined by the averaging, right? So we are getting the gradation coefficient for the first, second. I told we'll have the different properties. Suppose we have the 5 properties are there, we'll get the 5 gradation coefficients. Then we'll make the average. Then we'll get the gradation grade. So we are getting the gradation grade for the first material, second material, third material, fourth material, and so on. And which is having the highest value, so that would be the rank 1. So that material you have to select, right? So that is the best material available to you. So that can be used for the particular application, right? And sometimes what we'll use, here we are making the average, but sometimes we'll go for the dissimilar weights. So you need not give the same weightage for all the properties. Some properties are very important, so you can give the more weightage. Some properties are least important, you can give the lesser weightage, right? When you are giving the equal weightage for all the material, all the properties, then we can use the average. Normal average you can do. That indicates you are for all the material properties, you are using the same weightage, means you are giving the same importance. But sometimes you want some material properties you want to give the higher weightage, some material properties you want to give the lesser weightage. Then we have to use this formula, Wk into eta k, right? So the Wk indicates what is the percent of the weightage we are giving, and the total percent should be 100, and the total value should be 1. So this formula we will use when you are giving the equal weightage. This formula you are using when we are giving the different weightage. The weightage can be fractions, or we can give the percentage. The fractions is nothing but the percentages. Is it clear? Okay. Then we'll understand better when you do one numerical problem. Then it is more clear. So actually for the paper I selected 4 different materials, but for the time constraint I am explaining only one material. So for the selection of the gear material, so I am giving one example. This example is a grade for a gear material for high speed and high stress applications. So it is better rotated with high speed and high stresses are developed in the material. And this I have taken from one reference where the 9 alternative materials are available. So for this gear material, which is going for the high speed applications and high stress applications. So these were the practical application of this gear, right? And for that they selected the 9 alternate materials. What are the materials I can select for this gear, right? So it is not that much easy task. It is very difficult task, right? So they selected the cast iron, ductile iron, SG iron, cast alloy steel, through hardened alloy steel, surface hardened alloy steel, and carbide steels and nitride steels, and through hardened carbide steels. So these are the 9 materials selected, right? So they are shortlisted, and they are shortlisted based on some properties, right? So the overall performance of these candidate papers are to be measured with respect to the 5 material properties. So these are the properties required for this application. for high speed high stress applications. One is the core hardness, that is denoted by CH, and it will be measured in brilliant hardness number. So it will be given as a number, right? And surface hardness, so that is also will have the brilliant hardness number. And surface fatigue limit, so this is a fatigue limit that generally will mention as Newton per mm square. And bending fatigue limit, so this is a surface fatigue limit and bending, because whenever we will have the high speed and high rotations, so we will they undergo the fatigue loads, right? So the fatigue strength is very, very important for these applications. So the surface fatigue limit, Newton per mm square, and bending fatigue limit, Newton per mm square. And ultimate tensile strength, that also Newton per mm square. So you can see there are the different units are there, right? Some of the Newton per mm square, some of the only the numbers, brilliant hardness number, and core hardness also brilliant hardness number, right? So there are the different units and the numbers also will be vary. So that is the reason we'll go for the normalization, so that will not have any dimensions, right? So we make the dimensionless so that we can make the comparison, right? Otherwise it is difficult to make the comparison. Now out of these 5 criteria, so we mentioned the 5 criteria there. So the surface hardness and surface fatigue limit and the bending fatigue limit and ultimate tensile strength. So this they should be beneficial in nature. Beneficial means they should have the higher value. So I told some of the properties we want higher values and some of the properties we want the lower values. While the core hardness, because it is a surface, it will have the more speed and more stresses inside of the body of the gear material, it should not be that much hard, right? So we are giving that is a non-beneficial. So only one is the smaller the better, and remaining these 4 properties are the larger the better, right? I told that it may be vary from according to our application. Some properties we want the higher value should be there, and some properties we want the lower value should be there, and some properties we want some targeted value. But in this case, so these 4 are the larger the better, and the core hardness is the smaller the better. So this we are not taken, we are taken only the example from this, right? So they did a rigorous work, what are the properties required and what should be high and what should be low for these applications. And what we did is we used this GRA method to select the best material. And these are the values available. So this is from the design data books. They have these are the material collected, and based on what are the properties you selected and what are the values for this material. So for cast iron, the core hardness is 200. So the units already mentioned, it will be in the brilliant hardness number, right? Core hardness and the surface fatigue limit, there will be hardness number, brilliant hardness number. And remaining all will be in the Newton per mm square. So that are the units. So that is the reason I not mentioned here. So these are the numbers, right? So only we are making some data is available. So the data is available for the 9 different materials. Now what is our tedious task? From this 9 material, and we know these 4 properties should be larger values are better. For this, the smaller values are better. So from this data table, suppose you want to see from here itself, which is having the smaller value for the core hardness. Core hardness, the A9 is having the smaller value. So when you select only the core hardness, this material is the best for you, right? But here it is a combination of the properties, not a single property. Suppose you want for the surface hardness, right? Then if it is the higher the better. So which is higher? 750 is the higher. So only that property is needed, then this is the best value for you. Similarly, when you are going to the surface fatigue limit, we want the larger the better. So which is the larger value? 1500. So this metal is better. So A7 is better. For this A6, A8 is better. For this A9 is better, right? So they are conflicting in nature, right? So then it is a very tedious problem. Means what we have to do? How to solve this problem, right? So which is the best material for our gear to manufacture the gear, right? Suppose similarly you are going for the ultimate tensile strength. Again it is 2300. This is the larger the better, right? For this also this is the 920. So how we can select? Then we can go for this gradient relation analysis. So first I already told, now we will go for that calculations, normalizing the value, making the deviation sequence, then you calculate the gradient relation coefficients, then you calculate the gradient relation grade. So once you are getting the gradient relation grade, which is having the higher value, that will give the first rank, and that can be selected the best material for this gear application. So first we are going for this core hardness, right? And here what is the strategy we will apply is the lower the better, the smaller the better. the smaller the better. So smaller the better is 185. Then we are using the equation. For the smaller the better, I told we will have the three equations are there. We are using the first equation. The maximum value minus the particular value. Denominator will be maximum minus minimum. Right? So these are the values of for the different materials. This is for A1 first material, second material up to 9 materials. Now we substitute in the equation. Right? So this is xi of k. And in that available values, what is the maximum value and what is the minimum value. Right? So for the first one, it becomes the maximum is 315 minus this value is 200 by maximum is 315, minimum is 185. So when you calculate, it will come 0.8846. That is for the first one. And you will have some curiosity, what will happen for the maximum value and what will happen for the minimum value. What will happen for the maximum value? It will be maximum minus of xik. Xik is nothing but that particular value. So 315 minus 315, denominator is the difference, 315 minus 185. So it becomes 0. So which is having the maximum value? So this normalized value is becoming 0. Right? And which is having the minimum value? Right? It is becoming is 1. Is it clear? This calculation part is clear? Is this calculation part is clear? Okay. So we are making the maximum value minus xik and the denominator is maximum minus minimum. Right? So xi is in that part, you can use these values. These are values will be xi. When you calculate the first one, this becomes xi. For the second row, this becomes xi, and third row it becomes maximum value, which is the highest value in this, and minimum is which is the lowest value. So this is the core hardness. The smaller the better. Next you will go for another. We'll see another one also. The larger the better. For the larger the better, this is the equation. Xi okay minus minimum. Denominator again maximum minus minimum. And the surface hardness values we are taken from this table. These values we are taken. So 200, 220 and so on. In this, what is maximum? 780. And what is minimum? 185. So we are going for the second property. Right? That is surface hardness. The larger the better is required. And we are using the second equation. Sorry, actually this is the first equation. The larger the better. So this xik is 200. And maximum is 750. Minimum is 185. So 200 minus 185 by 750 minus 185. So it is coming 0.0265. Right? So for the first element, for the first material, it is 0.0625. And we'll see again for maximum, which is the maximum value, what is the value. So for maximum, it is getting 1. For minimum, it is 0. Because the larger the better, so maximum we are getting 1 and minimum we are getting 0. What is happening? Happening is 0 to 1. That only it is ranging from 0 to 1. Right? So we are normalizing between 0 to and 1. So we are doing two things. One, we are making that will be dimensionless. And second, we are making the values between 0 to 1. What are the values will be? Suppose it may be in 10,000s or lakhs also, or it may be in the fractions also. We are using only these values. So automatically they will come, what are the values are there? It is the higher values or the lower values. It will come only between 0 to 1. So that it can be comparable. Right? And these values, first property also we are making 0 to 1 only. Second property also we are making 0 to 1. Means all the material properties, irrespective of their actual values, now they are changing to 0 to 1. They are dimensionless and they are comparable now. Right? So we are doing the two important aspects in these steps. Right? Okay, now if you want, we can select the values. The same thing I calculated for all the things. For all the values I calculated. Right? So this you can see for the first one, 0.8846, 0 and 1 for 315 and 185. So that we calculated here. Right? 0.8846, then 1. Then 0, 0. So where is the minimum is there? The maximum is there 0, 0 because the smaller the better. Right? Similarly for surface hardness, first value is 0.0625 and which is having the larger value it is 1, which is having the smaller value it is 0. Right? So what is happening? All are coming between 0 to and 1. You can see the first property, second property also 0 to 1, third property also 0 to 1, fourth property also 0 to 1, and fifth property also 0 to 1. Right? And you may have the doubt, means it needs, suppose so many materials are there, how to make these calculations. Okay, let it be. I'll explain the remaining calculations also, then I'll show how we can use the Excel to do these calculations, Excel software to make these calculations simpler. Right? Okay, you are getting the normalized value. Then we have to go for that correlation coefficients. So before calculating the correlation coefficients, you have to go for the deviation sequence, how much they are deviating. from the reference value, right? So you are calculating the gradation coefficients. So what is the formula is eta of k is equal to delta minimum eta into delta max and delta of ik, so that is particular value, and delta eta into delta max. So these are the normal values which are shown in the table, and I have not shown the deviation sequence, but if you want for the reference I made here. So this is the delta, or we can say the deviation sequence, that is nothing but 1 minus normalized value. So subtract 1 from 1 minus this, then you get these values, and these values are using in this formula. So you are not using the normalized values. What are the values you are using? The deviated values. How much they are deviating from the reference value, right? From the 1. So 1 is the ideal condition, right, among these available. So 1 minus this normalized values. So these are the deviated values, right? And this is delta 0 ik, means for particular first one, first row, first material, this is the value I would use in the delta of ik. So this should be kept here. And similarly delta max. So in this, what is the maximum value? So that is 1. And delta minimum, that is 0. So delta max is 1, delta minimum is 0. So that is the reason I told this delta minimum, eta, delta max, this will be fixed. So this will be a constant when you are doing particular problem, right? And what is changing? The change will be only the denominator, because this value will change. For the first row, this is 1. For the second row, this is a value. And again, this will be the constant, because they are mentioning eta is equal to 0.5, right? So here I told eta can be changed from 0 to 1, but generally we use 0.5. I use 0.5 for this problem. So for the first element, it is 0.11535. So delta minimum is 0, eta is 0.5, delta max is 1. Means the numerator becomes always 0.5 only, right? Irrespective of different rows, different columns. And denominator will change. So denominator delta 0 ak, that is for first it is 0.11535 plus this is 0.5 into 1. So 0.5 by 0.6135. So this is 0.8125. So for this one, we are getting 0.8125. Then we'll see what happened to this 0. When you substitute here 0.4 into 1 and denominator also 0.4 into 1. So this highest value will not change. This highest value will not change. But this value is going to change. This value will not change, right? When it is deviated 0 from the reference value, it is 1 only. Even though you are keeping 0.4, 0.5, 0.6, whatever you keep, this value, right, where the normalized value is 1, the deviated value is 0. For the deviated is 0, it will be always highest value. Means it will be 1 only, irrespective of keeping eta value 0.4, 0.6. But what is happening this? For 0.4 it become 0.28. For 0.5 become 0.335. For 0.6 what it becomes? Anyone can respond? When eta value is 0.6, what it becomes? 0.375. Absolutely correct. So this is 0.375. Means what is happening? So this indicates we are not making 0 to 1, we are making some value to 1. Means this, instead of making the Relational coefficient 0, right? So which will not having any meaning. So we'll give some values. That is the reason it is, these calculations are called gray. We are not making it is completely 0, we are making some value, right? So that is happening. That is the importance of this eta. The eta can be given any value. If you are keeping the lesser value, this value becomes lesser. If you are giving the more value, this value become more. If it is becoming more, then what will happen? The gap between these two will, this smaller value to the larger value will be very small, narrow. Only that is the difference, right? If you are keeping 0, then you cannot solve the problem, right? So eta can be any other value. So you can keep 0.1, 0.2, 0.3 and so on. But generally for our application, you can use 0.5. So what are the value you are keeping? It doesn't matter much, right? Only this value will change, and this value, the highest value will be 1. And this also will correspondingly will increase, right? So the gap between that lowest value and highest value will be narrowed, will be reduced when you are increasing this value. When you are decreasing this value, the gap between this lowest value and highest value will be broadened. That is only the difference, right? You can use any other value. Is it clear? The calculation of the Relational coefficient. Okay. So once you calculate the Relational coefficients, now the solution becomes easy. You normalized, you got the Relational coefficients for the different properties. Now these are the Relational coefficients I calculated for all the things like this. For this one, 0.8125 and 1 and 0.33. Where 0 is there, 0.333, right? And where it is not deviated, it is 1. Means it is not deviated means it is highest value. It is not deviated anything. That is 1. Which is deviated should be given 0, but we are giving some gray value. Means some value, that is 0.33. If you are selecting 0.4, no, end result will not change. End result will not change. Already we have seen only the gap will change. Or you can take one example and you can check. I'll show how the end result will change. I'll show with the calculations. There will be minor change, but not major change. Okay, like this we calculate for all the elements, right? For one property I explained here. For one property I explained only the 3 elements. Like that you can calculate for the remaining. And for the second property, so I calculate for the co-hardness. Then you can calculate for the similarly with the surface hardness and surface fatigue limit. And all we are making from 0 to 1. Right? Minimum value is 0.333. If you are selected 0.6, it becomes 0.375. If you select 0.2, 0.4, it becomes 0.285. But maximum value will be 1. And this will change. This will increase a little. If you are selecting the lower value, this will decrease. But highest value will not change. Right? Highest value will not change. And only the gap will be changing. Okay, now what we'll do, we'll calculate the gradation grade. Means now what we are, all are comparable. All the properties are comparable. Right? Now we can take the decision. Now we can take the decision will be very easy. How we can take the decision? So we can take the decision based on whether you are giving the equal weightage for all the properties. If you are giving the equal weightage for all the properties, what you have to do? Add these all the values, divide with 5. But for this paper, what they mentioned, they did a lot of work for this material, and this Milan et al. He selected the properties criteria. For core hardness, the weightage will be 0.005. For surface hardness, 0.1720. For surface fatigue limit, 0.4. So it is highest value. So the surface fatigue limit, because the rotation, the fatigue strength is very, very important, right? And bending fatigue length is 29%. So when you making the percentage, it will be 29%, right? And this is be 10% if you multiply with 100. So here is chosen the different properties. Actually, this is correct. For all the material properties, we cannot give the equal weightage, right? Some material properties we want should be high, good value. So that will be given more weightage, right? And some will be given the lesser weightage, right? If you want to give this equal weightage, then just you can add these all the values, use the formula, add these all the values and divide with the, how many are there? 5 properties are there, divide with 5. But here what we used this one. So that is the reason we got this 0.3358. It is not the average of this, right? Don't misunderstand. It is, you are multiplying this, each one will be, first one is multiplied with 0.005, second one is multiplied with 0.1720, third one is multiplied with 0.2426, right? And fourth one is multiplied with 0.292, and fifth one is multiplied with 0.102, right? and we got the value 0.3358. Like that we are getting for all the materials, right? We have selected the total 9 materials, 9 alternatives are there. For 9 alternatives, we are getting the 9 values. Now after getting the values, we can give the ranking, right? So which is the higher value, that will be the first rank. So for this table, this is the first. After the first, so this is the second value. After the second, 0.443 and so on. And what is the worst will be 0.3358. So A1 material is worst, means it is not worst for our application, it is worst, but it may have its own applications, right? For our application, for the gear material, which will have the high speed and high stress applications, this A7 material, which is having the 0.67878, that is a relation grade. So that is the best alternative. Is it clear? Okay, I got the responses. Now I'll show these calculations. So this is over. Now I am saying the best among this availability. So it is not a best in reality, it is a good solution. It is a good solution, not the best solution. It is the best solution among these. Any doubt? It is the best alternative among these 9 alternatives. Right? There may be any other materials also, because we are not gone through that. Right? There may be other materials also that we don't know. But according to our data collected, these are the material available for that time. And out of the available data and materials, materials and their data, out of these 9 alternatives, this A7, that is the best alternative to make the gear material. And what is that material? That material is A7, is the carbide steel. So the carbide steel, which will have this core ordnance is 315, and even though this is 700, but these 3 properties are high, 1500, 920, 2000. These 3 are high. Even though these 2 are, this is not the lowest and this is not the highest, but till these 3 properties. Very important question. So that part I don't know, because they did the entropy method, some other methods are there, that is the material selection. Right? They utilize the entropy method to determine the priority weights. So these are another important theory concepts, how they can give the weightage. Right? If you want in detail, you can go to this paper in the reference. I'll give you what are the papers I published, that reference I'll give. So when you read this paper completely, then you can understand how they are giving the weightages. Right? Now our present topic is the gray relation analysis. Our present topic is the gray relation analysis. We have to focus only on this. Right? So you can go to the references to get in details. Right? But in our engineering application, what we are doing? We are not calculating the SN ratio. In this, we are not calculating the SN ratio. See, in these steps, we are not calculating the SN ratio. This is only normalized values. This is different. I am not using the Taguchi method till now. I am using only the gray relation analysis. So here we are not using the SN ratio. Right? So these are the available materials are there. I calculate only normalized value, then the deviation sequence, then I calculate the gray relation coefficient, then I calculate the gray relation grade. Out of the gray relation grade values, which is the highest value, that I selected as the best material. Right? Okay, now I'll show the Excel sheet, how we can do. There are so many things are available. How we can see, we can do the small Excel. You can do also, because already I did, I want to show the calculations. Okay, these are the calculations. These are the core ordnance. So what is, first we are making the normalized value. The formula is 315 minus that value, means the maximum value minus that value. And what is the denominator is the maximum minus minimum. So what I kept, 315 is the maximum value in this. But core ordnance, the minimum is the better. But formula is maximum minus that value by denominator is maximum minus minimum. That is the formula. Right? So first what I am making 315 minus 5. So I use the calculation. This is 315 minus, when you make the equation, this is 33. So I have to, you have tried is equal to 315 minus 33. So 315 is the highest value. So maximum value. So like that, once you calculate this, just you can copy and paste the remaining rows. Then the same formula will come. So you can automatically calculate. These are all the difference from 315. 315 minus 200 is 115. 315 minus 220 will be 95, and so on. And the next is, this is the normalized value. Actually, the normal value will be 315 minus that value by denominator is maximum minus minimum. In the gradation coefficient equation, what is the gradation coefficient equation is delta minimum plus eta delta max. Denominator is delta OI, means particular element, right, plus eta into delta max. So this is the denominator what I made here, that P plus delta 0.5. So P is this value, delta value plus 0.5. How we got this 0.5 is that eta into delta max. Eta we selected 0.5 and delta max is equal to 0.4. Sorry, delta max is 1. So it becomes only 0.5. So this is the denominator. Then we are making the final value. The final value is, what is numerator is delta minimum plus eta into delta max. Delta minimum is 0. Eta is 0.5. Delta max is 1. So it is 0.5. That I told it will be fixed. 0.5 numerator will not change. Denominator will change. That is the reason I mentioned in Excel sheet 0.5 by k. K is this value. This value is changing for all. But numerator is not changing, because the numerator is delta minimum plus eta into delta maximum. Delta minimum is 0, eta is 0.5, and delta maximum is 1. So it is 0.5, right? So 0.5 by k. So you are getting the gradation coefficients, right? So where this is 0, we are getting 0.333, and maximum we are getting 1. So the coefficients are varying from 0.33 to 1. And when you have selected some other value, already I told this will be, if eta is 0.4, this become 0.265. If eta is 0.6, this become 0.375. Right? Only this gap. And then what will happen? Not only this value, all other values will change. When eta is increased, they will be increased little. When eta is decreased, they will be decreased little. But this max value will not change. Only the minimum value will change. So what will happen? The gap between them will be narrow. Right? And when you are giving the lesser value, the gap will be more. So when you want to get a more precise values, more differential values for the different elements, then we can give the eta value less. But in general, we'll give 0.5, means in between. Right? Not too narrow, not too broader. That is only the intention. But we are not making a 0. That is the reason we mentioned it is a gray. Right? It's not completely 0. We know something. That is the meaning here. So like that I made the Excel sheet. So once you know the formula, the same thing will be here, but only the value will change. Here what is the minimum value? 185. So if for this all it will be maximum is the better. The larger is the better. Only the core hardness, the smaller is the better. For all other values, the larger is the better. Right? So that is the reason the formula will be y minus 185. 185 is the minimum value. Here y minus 330. 330 is the minimum value. The formula numerator is y minus the minimum value. Means that value minus the minimum value. Denominator is the maximum minus minimum. Denominator is constant to calculate the normalized value. Here maximum minus minimum is 750 minus minimum value is how much? 185. That is 185. Sorry, 565. So these are the normalized values. Then the deviation sequence. 1 minus the normalized value. Then this Graylish coefficients will have the denominator and numerator. The numerator is a constant, that is 0.5. Denominator only vary, that we are calculating. Right? The last step will be the complete value, that is delta minimum plus eta delta max, which is 0.5. Denominator is delta OIK plus eta delta max, that is the value, this one. So that is varying these values. So here also you can see the minimum is 0.33 and maximum is 1. So like that we can make this Excel sheet. So we are getting these Graylish coefficients. Right? After making the Graylish coefficients, I made another calculation. We have calculated the Graylish grade for the different materials. Different alter. Here we are. Okay, these are the values changed. So because we are 20% earlier, this value is from 0.96 something. It became 0.83. So that became number 1. Right? And which is second 0.63. So this will be second. This will be third. So there may be slight changes in the other ranking, but not the best ranking. Right? There may be slight changes. Sometimes there may be interchange some of the elements when you are giving the equal weightages. So that is up to you and depend upon the application. Right? Not exactly not up to us. Depend upon the practical application how we can give the weightage. So when you are giving the equal weightages, we'll have these values. When you are giving that exact weightages based on that paper, right? So we give the different weightages for the different things, for the different properties. Then these are the values. But in both the cases, the first material is same, right? The best material is the same. So it's not a vary, right? And other question what you asked, when you change this eta value, so this value will change. Then also there will be little changes in this, but I am damn sure they will not influence the best material. They may be changing the ranking, little ranking may change. They're not exactly sure, right? Depend upon these values, what are the values are giving and how they are influencing. It is interlinked. So we cannot ensure, right? Exactly we cannot say. response. We'll have only the single output we want to measure, right? Then we need not go for this GRC. Directly we can get the optimum parameters from Taguchi experiments only. But when we'll have the multiple response, right? Multiple properties outside output parameters you are measuring, and you are getting the multiple response. Then how to make the single response so that you can take the decision which experiment is the best experiment, or which parameters I have to use, which combination of the parameters I have to use. So for that, we are getting the multiple responses, and that responses will put into the correlation analysis, right? So the output we are taking from here. How we are getting the output? We are conducting the experiments. We are conducting the experiment based on the Taguchi model. Then calculate the signal to noise ratio, right? Then we are getting the responses, right? What the responses are getting. Then we'll get the best parameter for each response. What are the best combination for each response? But you want overall for all output parameters or output responses, you want what is the best combination overall. Then we have to go for this relation analysis. So again, we'll use the same steps whatever I explained. So relation generating, then the reference sequence means before that we'll get the normalization. Then we'll calculate the relation coefficient. Then we'll calculate the relation grade. So after the grade, getting the grade, will be only single response. So here itself we can select. But you want to select in that we will go for the which is the optimum factor and which is having the more influencing. We can do some more calculations if necessary. If you want, you can use this itself. But you want in detail on overall which factor is more influencing and what are the optimum conditions. You want some more analysis, then you can do this optimum parameter levels determination. So for this, I'll give another example of the work done by us. So this is the multiple process parameter optimization of YEDM of AICTE 304 using the Taguchi relation analysis. So we use the Taguchi method and we are using the relation analysis to find the best optimum parameters, right? And these are the different input parameters we used: the pulse on time, pulse off time, survey voltage, and dielectric pressure, then wire feed, wire tension. These are the parameters. So we'll have the 6 factors. So what are the input parameters? They are called factors. The terminology what we use is the factors, and output will say as a responses. And these are the levels. So we use the 3 levels. We use the 3 levels: 0.25, 0.75, 1.25, like that other parameters. So these are the machining units. In the machine they will mention this one, but actual value will be this one. And here I mentioned what are the units. So one is in microseconds, another in voltage, and kgs per centimeter square, and these are the meter per minute. So these are units. Then we'll go for the design of experiments. So that part also I'm not discussing, right? So we mentioned L27. That is the experimental design what we used. So these are the 27 experiments are there, and these are the combinations. So these 1, 2, 3 indicate the levels: first level, second level, third level. And what are the values are be? These are the values. First level, this value, right? These are the first level values, these are the second level values, these are the third level values. So total we conducted this 27 experiments, right? Then we got the responses. So then we measure the output parameters. The output parameters, the output responses. One is the metal removal rate, another is the surface roughness, and the last one is the dimensional deviation, right? So these are the values obtained from the experiments. And earlier cases we got that material properties from the design data books or somewhere. But here we have to conduct the experiments to get these values, and we have to measure it. It's not that easy task, it is a difficult task. Again, we have to measure the surface roughness. Again, we have to measure the dimensional deviation. How much did they deviated from the actual dimension? What is the dimension we are intended, and what is the deviated, how much it is deviated, right? So these are the responses, and you can see the 3 responses are the three different units. One is in mmQ per minute, another is in micrometers. So these are very small value, and this is in mm. One is in mm, another is in microns, and another is mmQ per minute. This is the volumetric removal rate. Multiply with the density, then we'll get the weight, right? So here MRR nothing but VRR actually here. So again, these are the 3 different units. Then this part you may be knowing, right? I will not go in detail. So when you go for the normal Taguchi method, we'll go for the SN ratios for all the 3, the responses. Then we'll get the optimum parameters for MRR. So these are the parameters we got. Optimum parameter for MRR only for one response. So A3, B1 means this is the first parameter for the third level. B1, C2, D3, E3, F3, right? So these are the optimum parameters for MRR, right? Similarly, you can calculate for the surface roughness. So for the surface roughness, these are the optimum parameters, right? So surface roughness, what we want, the metal removal rate, we want the larger the better. when you do the machining, we want more material should be removed the lesser time, so that we can save the time, right? So the metal removal rate, the larger the better. That is a characteristic what we want to use. And for surface roughness, the smaller the better, right? So I'm not talking the surface finish, it is the surface roughness value. It will be measured in microns, so the roughness value should be lower. So for this, the smaller the better characteristic we'll use. So what are the optimum parameters? A1, B3, C3, D3, E1, F1, right? Similarly, we'll have the optimum parameters for the dimensional deviation, how much it is deviated. So here also it should not deviate much, so we want the smaller value. So the smaller values, these are the values, the optimum values: A1, B3, C1, D1, E1, F1. So they are not the same, right? For all the cases, we are getting the same combination. Then we need not do any further analysis, because all are giving the same, and we want all the conditions are satisfied. We are getting the maximum metal removal rate and lower surface roughness and lower dimensional deviation. For all the cases, we'll have the same combination, but it not so. We'll have the different combinations are there, right? So we cannot take the one of the experiment without combinations. Then what we'll do? For a single response is okay, right? For MRR, you can use this combination. For only if you are bothering only surface roughness, this combination. If you are bothering only for the dimensional deviation, this combination, right? But we want all should be there. So we want the multi-response optimization, right? Or multi-output optimization. We are going for the gradation analysis. So I am not going the calculation in detail, because already explained for the problem earlier. So here we'll have the 27 combinations are there, right? And already I told we'll have the metal removal rate, that is in mmq per minute, surface roughness in microns, and dimensional deviation in again mm. These are the three different units. What we have to do the first step is make the normalization, use the formula, and here what we are using, MRR, we are using the larger the better, surface roughness and the dimensional deviation, the smaller the better. So use the corresponding equations, right? So we'll get the normalized values first, then you make the deviation, that is delta value. So delta value is 1 minus normalized value. Then you can calculate the gradation coefficients. So when you are calculating the gradation coefficient, you can use that formula, that is delta minimum plus eta into delta max, denominator delta OI plus eta into delta max. There you can use eta value 0.5 or 0.4. Generally we are using 0.5, you can use 0.5. So we use 0.5 only for this whole equation, right? So I got the gradation coefficients for these values for all the 27 experiments you have to calculate. And earlier we calculate for the 9 material, but here we will have the 27 experiments, right? Because of the Taguchi method, we got the 27 experiments, for the 27 values we got. So similarly for the surface roughness, we will have the 27 values, and they are varying from 0.33 to maximum 1. That I told. So when you select 0.5, the minimum value will be 0.33. If you select 0.4, it will be 0.265. If you select 0.6, it will be 0.375. And correspondingly, this value will change, but highest value will not change, right? Similarly, we got the surface roughness, right? The maximum value is 1, and similarly, we'll have the dimensional equation. Then we calculate the gradation rate. Here, what we used the normal method. We made only the average. We gave the equal weightage for all the three, but it's not necessarily. So, you can give more weightage for metal removal rate, lesser weightage for the surface roughness, and still lesser weightage for the dimensional deviation. That is up to you. But in general, we will give the equal weightages. But you have to give justify. Suppose you are giving the different weightages, you have to give the justification. If you are giving the equal weightage, generally they will not ask any what is the justification, right? But in general, if you want to give the metal removal rate, you are giving the more weightages, right? Then you want I want to make the production will be faster with a lesser time I want to complete. Then you can go for this way. You can give the more weightages. So for these problems, I give the equal weightages for all the things. So I gave the equal weightages for the three properties. I gave the equal weightages. So it is the average of these three. So this plus this by 3, right? So you are getting the gradation rate. So from the gradation rate, you can select which is highest. So 0.7494 is highest, right? So this is the best the parameters combination, right? So what are the 7th experiment is there? That combination. So here totally we will have the 27th experiment is there. That combination is the best combination. There are optimum parameters, right? Optimum parameters for the maximum metal removal rate and maximum surface roughness, means minimum surface roughness and minimum dimensional deviations, right? It is optimum. I'm not telling this is the best. It is the optimum parameters. But when you talk about this is the best among these alternatives. These 9 experiments, this is the best, right? 0.794. But if you want to do further analysis, right, which is more influencing, which is actually you want to improve further, still you want to get much more better, then we will do the Taguchi analysis, the SN ratios for these values. So now we are taking the gradation SN ratios for the gradation grade, right? So we are taking SN ratio for the gradation grade. Then again we'll make these optimum parameters, right? So these optimum parameters A1, B2, C1, D3, E3 and F3. So these are the optimum parameters by calculating the SN ratios and making the main effect plots for the means, right? And gradation grade, you want that should be greater value, larger the better, right? The grade value should be larger the better. So while selecting also, we are selecting which is the higher value, that combination are selecting. So when making this analysis also, you take the larger the better, right? And there is some equations are there, we can predict, right? So when you are predicting, this is the formula A1, B2, C1, D3, E3. These are the averages at these levels, right? At the first level, what are the averages, right? How many experiments are conducted? What are the averages of that? Relation coefficients, grade values, right? And B2, C1 minus 5T. T is nothing but the average of the gradation grade for the corresponding all 27. So all 27, when you make the average, it is coming 0.6. So what is the gradation grade predicted is 7.537, right? So this is the predicted. But with this combination, you can do the experiment also. So that is called testing, right? So we'll do that is called confirmation experiment. So we'll do the confirmation experiment based on these combinations, right? So from this we got this is the best combination. So with this combination, then we made the experiment, then we got these values. Again, so once you got these values, then again we can calculate the gradation coefficients. And again we can calculate the gradation grade. So that value we got 7.7587. So this is 0.7537. So it is nearly same. So what is the predicted and what is the we got from the experiments that are almost same, nearly same, only with the 5% deviation, right? But it will not exactly match. It never matches. There will be some deviation. So now these are the optimum conditions for the Taguchi method. For the Taguchi method, for the different responses, for the material removal rate, this is the combination 31233. For surface roughness 133311. Right? For dimensional deviation, it is 131313. So for individual responses, these are the optimum parameters, right? Optimum factor parameters combinations, different levels. For overall gradation analysis, when you are making for the three responses, by giving the equal weightages for the three responses, this is the best combination or optimum combination. We'll say best, but it is not best, it is a good solution. Is it clear? The calculation part I have already explained. But how we can use for your experiments? For single response, you can go for Taguchi method. But whenever you have the multiple response, you can go for this. There are so many other methods also there. I'm not saying there are other methods are there. So there are so many methods are there, multi-criteria decision making methods. So many methods are there, right? And when you are making one method, then you can use any one of the two methods and you can make the comparison. Right, which is better? Actually, that also I did in some of the papers. I'll show. So one of the students they told what combination you can use or what is better. Gray fuzzy material selection. Okay, I use the gray fuzzy method for multi-criteria decision making method. So for this example I am giving, there is a preferential ranking method is there, utility concept method is there. Is it visible? No. Okay, here I compared any other. Actually, I did for the different materials. I'll give this in the case study. The gear material is one, and load bearing wagon wheels, that is the second experiment, second comparison, and insulation material, I think 3. Okay, here I can give that comparison between your method and with other methods. Where I give the comparison. Okay, right. The same problem they solved in the literature view. They solved with utility concept method, desirable function method, Topsis method. And when you calculate with the different methods, then we'll get the ranking, right? Then based on that ranking values, you know the rank correlation coefficient, right? So based on their ranking and based on your ranking, your method ranking, they can make the coefficient. The rank correlation coefficient. So I got for my method with these other methods, with these 4 methods, with preferential ranking method it came 0.9883. Means this method and that method are matching 98%, right? And the desirable function and this method almost are matching. So what are the method we used and what are the methods earlier researcher they used, right? They are almost giving the same results. When they are giving the opposite results, then we'll get differently values, almost -1. You know what is the correlation? This Spearman rank correlation coefficient, right? That is 1 minus 6 sigma d square by 1 n into n square minus 1. That is the formula we can use, right? And that will give what is their ranking and what is your ranking, and make this, right? When they are exactly matching, then we are exactly correlated, then we'll get 1. Nearly correlated, we'll get 0.5 to 0.7. More than 0.7 is a good strength. So I got these values. So one of the students told we can use other methods also. So no problem, we can use what are the method you like, which you feel easier, which is giving the good results. You can use method, and you can compare with other methods also. What are the methods available, right? So this is about using the Taguchi method, clubbing with the Grell analysis. Is it clear? I'll go another example. Is it clear? Okay. Okay, then other one will be similar to this. What are the experiments we conducted? This is a case study. This is published in the Taylor and Francis journal. This is a Scopus Index journal. So effect of sensing mechanism and machine performance on the ECDM process. So this is another manufacturing process, ECDM process. That is a hybrid non-traditional machine process. The combination of ECM and EDM. That you may be knowing. This is the experimental setup, right? And here what we used, here also we used the gray fuzzy reasoning grade. So we use the gray fuzzies, not only gray. That fuzzy logics I am not discussing now. It may be there in some advanced course they may conduct once again. I'll discuss only the Grell analysis, little about the fuzzy. So here we use the input factors and levels. So we use the different voltage, NOH concentration and duty factor. So these are the inputs or factors. And we use the 3 different levels. 3 levels are there, 1, 2, 3. Right? And here we conducted a L-line orthogonal array. So we'll have to conduct 9 experiments. And these are the parameters. What are the parameters we used? Right? And here what we measured after doing the experiments, we measured the metal remole rate. We are interested in metal remole rate, all the traditional, non-traditional machine process. And what is the radial overcut? So I'll make the holes, and what is the overcut, how much it is deviated. Right? So again, these are the output responses. These are the 2 responses we are interested. Right? Not a single response. Single response, you can go for the normal Taguchi method itself. You need not go for the Grell analysis. Right? Any multi-criteria methods not necessary. Right? So here MRR is there and ROC is there. So MRR we want, it should be maximum. And radial overcut, that is the deviation, how much it is overcut, that should be minimum. Right? So one credit should be maximum, another credit should be minimum. And these units are different. Right? So then what we did, we calculated the normalized values. What are the steps I explained? The same thing is there. First we calculate the normal values. So they should be vary from 0 to 1. Right? Then we'll make the deviation sequence. Then we calculate the correlation coefficients. So we calculate the correlation coefficients. So these are the correlation coefficients. Here also we used 0.5. That is the reason minimum value is 0.33, maximum value is 1. If you use 0.4, this minimum value will become 0.265. If you use 0.6, it becomes 0.375. That is only the difference. When you change these changes, automatically these other values also will change, increases or decreases. But the max value will not change. So we calculate the correlation coefficient for this. And MRR, the maximum, the larger the better. ROC, the smaller the better. So we have to use the 2 equations to get the normalized value. After getting the nominal value, we go for the deviation sequence. Right? How much it is deviated. That is the delta. So once you know the delta, then we can calculate the correlation coefficients. So once you know the correlation coefficient, then you can calculate the correlation grade. So we calculate the correlation grade. So these are correlation grade values. So after getting the correlation value, which is the highest value, that is the best parameter. Right? So this is the best combination or optimum parameters for getting the higher MRR and a lower ROC. And I use the gray fuzzy reasoning grade. So whenever these are some uncertainties are there, when you use the correlation analysis, to make somewhat more confirmation, you use some fuzzy logics. Right? So that part I am not want to discuss now. Right? So we'll use some fuzzy rules and fuzzy logics. Right? So we calculate that also. Based on that equation, that values, we made the ranking. But this value and that value doesn't change much, only for the ensuring. Right? So just like double ensuring, we'll do the fuzzy logics. So these are the fuzzy logic what we used. So you have to give the membership functions, who may be knowing the fuzzy logic, they may understand. So I use the lower value, minimum value, higher value, and highest value. So the lower value we defined 0 to 0.3 and the lowest value 0.3 to 0.5, like that. And this is for MRR and ROC. For output, we give some more precisely. So we mentioned lowest, very lowest, right? Medium low, low, high, medium high, higher, medium higher, then highest, right? So they will be very narrow. Then we'll give the fuzzy rules. So what is the fuzzy rules? We'll give when what is happening, right? When this values, this is lower, what is happening to this, right? When MRR, this is medium, this is also medium, what is happening to this? So we'll, based on this information, we'll give the fuzzy rules, right? So after giving the fuzzy rules in that MATLAB, so I'll give the membership functions and fuzzy rules. Then we can see we can substitute the values. So when you substitute the values, MRR particular value, then we'll get the output. So the output value will get, that is the GFRG value. So you got the GFRG values like this. So this is for one experiment, 9. This is the GFR value. So this MRR, this value, right? And the ROC, these values are there, and the GFRG value, this one. So that is a fuzzy logics. So to ensure whether GFRG values, GRG values, or GFRG values are nearly same. So we got the nearly same, right? So then we can give the ranking 1. Because already the gradation analysis, so many papers published there. So we want to make somewhat more refined by using the gray fuzzy reasoning grades, right? Then if you want to do some more analysis, you can do. Either you can use GRG values or GFRG values, right? So you can do some ANOVA, right? Then we'll give the values of F values, P values, and you can make the response tables. The response table will give which is a more influence parameters. So here it will give only which is we can select, right? So this combination will not give more details. This will give what is the optimum combinations to get good MRR and lesser ROC. This combination is best, but you want which is more influence parameter out of this, right? We'll have the 3 input parameters, are there, different input parameters are there. Which input parameter is more responsible, right? So here that is a response table. So voltage is in the first rank, right? So this is a more influence parameter. Then we'll have the electrolyte concentration, and the duty factor is in the lesser influence, right? And what are the optimum parameters? The best parameters, the combination is it should be 45, 30, and 70. This is the best combination. So this is the another case. And we did one more case, means what are the papers I published on this concept. So that only I'm explaining. So I did another case study, that is optimization of the selection forming depth and pressure of a box shaped superplastic forming by using the gray-based fuzzy logics. Here also is the gray-based fuzzy logics. And here what we want to optimize, the forming depth and pressure in superplastic forming. So this I did with Dr. Anjaya and with some students. And it is a conference paper and published in IOP, I think Material Science and Engineering. And one paper in SCI, another is paper in Scopus. These are Scopus index journals, but these are based on the conferences. 2 papers are the journal papers actually. And these experimental setup. So here the superplastic forming, just only send the inert gas, that's all. So you can send the inert gas and we can get the components, but the material should be superplastic nature. And here what is the problem is, when you form it, how much forming time? Here what we are interested is what is the forming time. It should not be, it should be less, right? And there will be thinning. So what will happen when you form, the thickness at the ends will be okay. Suppose you are taking the thickness of the sheet 3 mm, at the end it will be 3 mm only, but at the bulge at the top, at this apex, it becomes more thinning. There is some logic here, right? So that I don't want to explain. The thinning will happen. That is inevitable in superplastic forming. There are so many techniques how to reduce this thickness variation. So you cannot expect the same thickness throughout the component, right? The more will be thickness at the here, and thinning will be at the last, where it is forming the last. That will be more thinning. So we are making the thinning ratio. So the thinning ratio also we calculated. So there are 2 important things we are interested, right? And these are the parameters, right? Here also we use the L. So we made the depth is 10 mm, with the depth of the component, how much depth you are forming. So 10, 12.5 and 15 mm. So this is 15 mm thickness, the depth. And we use the different pressures, 30, 34 and 37.5. And we observe the forming time and the thinning ratio, right? So these are our responses, and these are the input parameters, right? And these are the responses, forming time and thinning ratio. and forming time is 37, and what is the maximum is 63. And thinning ratio, the maximum is 0.775 and the minimum is 0.305, right? But what we want, we are interested, the forming time should be lowest. So it should be as low as possible. The lowest is 21. And thinning ratio should be highest, right? So thinning ratio highest means if it is 1, the thickness at the starting at this apex, the thickness at this starting at this apex, both are same, then it will be 1. If this is very less, and this thickness by this thickness, the thickness of this last formed part, the portion to the initial portion, that is called thinning ratio. If it is 1, that is good, but it will not so, it will decreases. So this thinning ratio should be highest. So here totally different. Here this forming time should be lowest value, the minimum value, and the thinning ratio should be higher value. So two different approaches are there. So for this also we made the relation grade, right? We use the first we calculate the normal values, then we calculate the deviation sequence, then we calculate the relation coefficient, then based on the relation coefficient, then we calculate the relation grade. Here also we give the equal weightages, and for this problem also we used that eta value is 0.5. So you can see 0.33 is the minimum, 1 is the maximum. That itself indicates what is the eta value we selected, right? So we selected 0.5. If you select 0.6, it will be 0.375. If you select 0.4, it becomes 0.265. That is only the difference. But they will not be changing the highest value, right? Only this lowest value will change. That indicates you know the more information. Gray means 0 means it is no information, but that is not possible, no. So that is assuming this much information is available. That is only the meaning of the eta. So you can give the more higher value, but generally you can keep 0.5 without deviating the literature review. Right? What are the literature available? We are using 0.5, but that is not mandatory. You can use the other values. So we calculate the relation grade, and this is 0.9. So this is the best combination, right? And we made the gray fuzzy reasoning also. We use the same fuzzy logics, whatever we used earlier, but here we have the two responses. So membership functions for the forming time and the thinning ratio, and this is a membership function for the relation grade. And for this experiment you got 0.846, and with the GFRG value it is 0.78, GFRG it is 0.846, right? And we did not do same ANOVA calculations. We mentioned only this is the optimum parameters. These are the optimum parameters to get the lesser time and higher thinning ratio. This is the best combination, right? That is experiment number 3. What is experiment number 3 is the depth is only 10 mm, right? And the pressure is 37.5. So for superplastic forming with the normal convention forming, you should not go for the larger depth. When you go for the larger depth, it will be more thinning, and sometimes it may fracture also. It already become only 0.3. If you select the 3 mm, it will become 1 mm, and after that it becomes 0.5 and so on. So if you go for more depth, then it ruptures. That is the problem in superplastic forming. So you should not go for the larger depth. The larger depth is there is another method is there, that is called bulge forming. So you'll form it again, reverse it again. That is somewhat complex method, but we can do, right, for a larger depth. And there is other methods also. When it is material not superplastic method, then there are so many other manufacturing methods are there. The deeper components how we can form. But superplastic forming, this is the problem. When you go for the larger depth, there is a problem of more thinning, right? It may becomes very small also. Sometimes may rupture also. So there may be failure of the product. So that is very important, crucial in the case of the superplastic forming, right? And we got this is the optimum combinations. So depth you have to keep lowest, and the pressure will be highest, so that the time will be reduced. Because you are interested in the two things, the forming time should be less. At the same time, the thinning ratio should be higher. The thinning ratio higher means it is now nearly equal to the initial thickness of the workpiece.
Good morning, sir.
Good morning.
Sir, actually, I want to ask when we are selecting eta for calculating delta.
Right.
And then we have to consider the responses, or it doesn't matter whether the responses are 3, 4, or 5.
No. It doesn't matter with responses. It only matters. It will be what will happens. The max value and minimum value, it will be either wide dense or it will be narrow, and it does not depend upon how many responses are there.
Okay, we can choose any arbitrary value, whether 0.5, 0.4 or 0.6.
Right. Any arbitrary value you can use, but only because if you use 0.5, you can use some reference, because earlier researchers also used the same thing. We are using the same thing.
I
But-
have studied some paper, but it was not mentioned there how they have selected 0.5 value.
Okay. They'll not mention. Because that is arbitrary value, no. So most of the researchers, what they'll do, they'll read some previous research papers, and whatever they choose, and they'll use the same thing.
Okay.
If you go in depth and you do some calculation, then you'll come to know what will happen if you change. So what is happening if you change? It is ranging from, if you are keeping 0.5, it is ranging from 0.33 to 1.
That I have listened in your lecture, that by changing the value, how that is changing.
That's all. But it do not influence other responses. It does not depend upon how many responses.